It's a beautiful day in this neighborhood, a beautiful day for a neighbor. Would you be mine? Could you be mine? It's a neighborly day in this beauty wood, a neighborly day for a beauty. Would you be mine? Could you be mine? I have always wanted to have a neighbor just like you. I've always wanted to live in a neighborhood with you. So let's make the most of this beautiful day. Since we're together, might as well say, would you be mine? Could you be mine? Won't you be my neighbor? Won't you please? Won't you please? Please won't you be my neighbor?
Good morning, everybody. Welcome to Tibbet's Physics. What is crappinin'? Today we are going to continue our discussion of Einstein's theory of special relativity, and we're going to look at the formulas for time dilation and length contraction. To do this, we're going to look at our images of a train moving to the right from the perspective of somebody inside the train. O sub t is the observer inside the train. O sub s is the observer outside the train. For the person inside the train, because they are at rest relative to their clock, or light clock we could say, we could see that from their perspective, the clock or light just bounces up and down, and it's going to tick normally. To calculate the time, we could start with the formula v equals d over t, since the train is moving at a constant velocity, which means the time will be d over v, the velocity. In this case, the light travels up and down, so if d is the distance to go up, then 2d is the distance to go up and down. Our distance will be 2d, and then the velocity, since we're looking at a beam of light traveling up and down, we could use the speed of light, which is c. We're going to define this time as the change in proper time. We'll call it delta t prop. So why don't we define proper time before we move on? So proper time. That's delta t prop. Subprop. Proper time is the time measured by an observer that is stationary relative to the clock. Sorry. That is stationary relative to clock. In other words, when we're talking about proper time, we're looking at which person is looking at the clock. So if the person inside the train is looking at their clock, since they are stationary relative to the clock, because they're moving together, that is their proper time. If the person on the outside of the train is looking at their clock, they are also stationary relative to their clock, so that's their proper time. When we are analyzing questions, it's important to identify which observer is measuring proper time. Are we looking at the person inside the train and their watch? Or are we looking at the person outside of the train and their watch? So just read carefully on whose watch we're looking at. But the key idea is that if the person is stationary relative to their watch, then it's proper time. Their proper time. Let's look at the stationary observer on the outside and the time they're observing of the person moving on the train. So as we know, because the train is moving to the right, the light beam inside is going to bounce up and down like a diagonal. just like we saw as a person moving on a chair and throwing the ball up at the same time. From our perspective, the stationary person's perspective, we saw the parabolic path. Let's take this picture and zoom in and label a few things to come up with an equation that'll help us determine by what factor, by how much does the time change. So here we have our triangle. This is the light bouncing up, and then the light bouncing down, and we'll just complete our triangle. This triangle is going to be for measuring the distances. Right away, we know that the height, if we split this up in half, we know that the height that the light travels is d from the picture of the observer inside the train. We also know that the train is moving to the right. So if we want to calculate the velocity of the train, we know v is d over t, and the distance will be v times t. But since if we're only going to look at the halfway mark, we'll say the distance is cut in half. So on the left side, on the horizontal line, we have v times t over 2. And then for a diagonal, we have the same idea, except we're dealing with the speed of light. So the distance the light travels from the bottom to the top will be the speed of light times the time it takes all over 2. So c, and these should be delta t's. So let's change it to c delta t over 2 and v delta t over 2. We can see that we have a right triangle, which means from here to solve for the time, the change in time. So why don't we just do that? So we have a squared plus b squared equals c squared, which means in this case, d squared plus v delta t over 2 squared will equal c delta t over 2 squared. We'll expand this out. D squared plus v squared delta t squared over 4 equals c squared delta t squared over 4. Our goal is to isolate delta t, so let's get delta t's on the same side. D squared equals c squared delta t squared over 4 minus v squared delta t squared. Both of these have a 4 in common. So we could do 1/4, since it's on the bottom, times c squared minus v squared times delta t squared is equal to the distance squared. Let's multiply both sides by 4. 4d squared all over c squared minus v squared is equal to delta t squared. Let's square root both sides. That'll leave us with 2d on the top all over the square root of c squared minus v squared equals, so we square rooted both sides, delta t. Now we have to do a little bit of math trickery. What we're going to do inside the radical is multiply both parts by c squared over c squared, which means we have 2d all over the square root of c squared over c squared, which is 1, times c squared, minus c squared over c squared, also 1, times v squared. And that equals delta t. Since both sides, since the c squared and the v squared that we started with, both have a c squared in common, we can pull that out and take the square root of c squared. So that'll leave us with 2d all over, we're taking the square root of c squared from both of them, since they both have it in common. So all over c times the square root the c squared over c squared becomes 1. So 1 minus, we have v squared over c squared, which is v squared over c squared, equals delta t. If we scroll up to the top, we see that the change in proper time is 2d over c. And down here we have 2d over c. So we could change that to change in proper time, which leaves us with delta t is equal to delta t proper, that's 2d over c, all over the square root of 1 minus v squared over c squared. And this delta t on the left side is our dilated time. Which is the time that slows down, so it's a slower clock. What dilated time means is, let's look at our observers on the train. The stationary person on the outside, let's say their proper time is ticking normally, so it's just going up and down, normal time. And then the person on the train, if we time them, we can see that time takes longer from the stationary person's perspective. So what was 1 second for the person stationary appears to be longer for the person that's moving. So time is slowing down, or it's getting stretched out, we could say. Which means when we do the math, that the dilated time is going to be a larger number than the proper time. And again, it's very important to look at which perspective, from whose perspective are we observing, and from whose clock do we have our measurement from. Is our measurement from the proper clock, the person that's moving with the clock and appears to be stationary relative to the clock, or do we have the person that's moving away from us, their time? So it's very important, again, to define whose dilated time is whose, and whose proper time is whose. Okay, so now that we have time dilation, let's look at length contraction. To analyze length contraction, we have to look at the scenario of the train from both perspectives, the person outside the train and the person inside the train. Let's look at the perspective of the person outside the train that sees the train moving to the right. From their perspective of the stationary person, their time is traveling normally. And let's say they want to measure the distance the train travels at some given length that they could just measure with a meter stick. And that the train is moving at some speed v. Since we can just measure this length with a meter stick, I think I need some more water. Since we can just measure this length, we're going to call that the proper length. And let's define it as the proper length. So the proper length we'll call L prop is similar to proper time. It's the length measured, or the measured length, the measured length by an observer at rest relative to the object. So that length is the proper length. What we can do is we can calculate the time it takes for this person using our velocity formula. V is d over t. And let's use the proper notation. We'll solve for the time. So we'll say delta t is the distance over the velocity of the train. In this case, the distance is the length of the train travels, or L prop. So delta t is equal to L prop over the velocity of the train. Now what we have to do is look at the motion of the train from the person's perspective inside the train. So let's redraw the picture. Inside the train, we have our observer and the stationary person, and I guess we could say the proper length, are moving towards the person in the train. Or sorry, moving away from the person in the train, or to the left of it, so in the opposite direction. So what we want to do is figure out what happens to the length that the person inside the train travels from their perspective. Now from above, if we're looking at the person's perspective inside the train, their clock is just moving up and down, which is the proper time. So we can say delta t prop, that's going to be a faster time relative to the observer's time on the outside, the stationary observer, is equal to what length they travel over the velocity. In this case, the velocity is the velocity of the stationary observer, but we're saying that the observer is moving to the left. Both V's are the same, it's just from a different perspective. The V on the left is the train moving to the right. The V on the right is the stationary person moving to the left. What we ultimately want to do is calculate what happens to the length of the person, the length that the person in the train travels. So let's first solve for L on the left side. So we have L is equal to delta t prop times the velocity. The other equation, we see that there's a velocity, so let's get V by itself. V is equal to L prop over delta t. Wherever we see a V, let's plug in proper length over delta t. That leaves us with L equals the change in proper time times V, which is the proper length, all over the dilated time. And from above, we learned the formula for dilated time. It's the change in proper time over 1 minus V squared over C squared. So let's plug that in. L equals the change in proper time times the proper length all over delta t, which is delta t proper, over the square root of 1 minus V squared over C squared. We can see that our proper times cancel out, and we have L proper over a fraction, so we're going to do state change flip, which means the length is equal to L proper times the square root of 1 minus V squared over C squared. This length L is the length contraction. And this is the length contraction as a result of the moving object. So it's going to travel a shorter distance due to the fact that it's moving. So length contraction is the length contraction of the moving object. What's important to note is that the proper length is if you just took a meter stick or a ruler and measured something without moving, that'd be L proper. The contracted length is how much does that distance or length shrink as a result of an object moving relative to another. we'll do a few math problems in the next video, but that's it for now. Thank you for watching, and I'll see you next time.